Hello viewers, this is Kissy and welcome back to my channel. In this part of my tutorial series working with step 7, I will walk you through how to use bit logics, comparators and converters in step 7. Let's get started. So I will move to step 7 and open OB1, and on our left side we have a catalog that is having our bit logic, our comparator and then the converter. So the first item on our bit logic is the normally open contact. So I will insert it on our network, and basically the name normally open indicates that by default this contact is always as logic 0 and it will only move from logic 0 to logic 1 when the address that this contact is assigned to transition from logic 0 to logic 1. So basically we made use of this normally open contacts in our direct online tutorials, and we realized that you can series this contacts to either create any number of AND gates input that you want to create. So if I series 3 of them, then I can create what we term as a 3 inputs AND gate. So the next item is our normally closed contact. The normally closed contact is basically the opposite of the normally open contact, because with the normally closed it means that its logic state is always by default is at logic 1, and it will only transition from logic 1 to logic 0 when the input that it has been assigned to receive an input signal, or when the internal relay that is being assigned to changes from logic 0 to logic 1. So we'll have a look at an example. Let me put a call in here, and then I will name this one as i6.0, i6.1, i6.3. So basically I've placed in this contact and I've assigned an input address to them. So if I'm having my output call, which is, let's say, KO6.4, okay. So we are saying that we want to analyze these circuits, which means unless this contact closes, and then this one closes, and this one closes, and this one also remains at the normally closed position, then we can energize this particular contact. So now from our simulator, we can illustrate this particular contact receiving signal by ticking this box, and then when we untick, it means that it's not receiving signal. So I will save it and download this quickly into our PLC, which is our simulator, and then I'll put the simulator into run mode, test our circuit. I can now go online, and then we can analyze this contacts that we are referring to. So we can see that by default the normally open contact is open and there is no current flow through it to this section of the code, and by default our normally closed contact is closed. So what we are trying to explain is that the normally open contact will only change state when the input receives signal. So the input 6.0 will receive signal, and we can see that it has changed state from normally open to closed position. And then the next one is 6.1 also receiving signal, 6.2 receiving signal, and immediately 6.2 received signal, it went through 6.3, and then the output energized, which indicates that 6.3 by default is always at logic 1, and it will only move from logic 1 to logic 0 when the input card receives signal. So 6.3 will receive signal, and we can see that it has put. So 6.3, which is the normally closed signal, always serve as an inverter that can invert the signal that is coming your input card, or the signal that is coming to the internal memory location where we have assigned to this particular input. So I'll go offline, and then we continue with our bit. The next item on the list is our NOT logic, and we are saying that the NOT logic always inverts a signal and input signal that you are sending. So if the input signal is at logic 1, then the NOT signal will invert it to logic 0. So we can illustrate that by placing the NOT signal at this particular point, and then we can see that all the signal that comes from the side, if they are all at logic 1, then it can invert it to logic 0. I will put the NOT right here to illustrate how it works. So I click on save, download. It will already exist, so I will say yes, it should go ahead and override. I go online, put on the goggles, and we can see that our signals are all ticked, and then when it got to this section of our code, the logic 1 that we are having here, that we are expecting to go through up to the input I6.3 has been inverted. So we can see that this section is off. Let me turn on 6.3. Was receiving signal, now I've taken the signal off so that it goes back to its default state, which is normally closed, and we can see that we have no signal going through to energize our code. So basically the NOT can be used to invert any signal. So with this explanation, we'll move on to the next. Our next is going to be our output call, and basically we've already made use of this output. So whenever you want to write to the output card, you can bring an output call if the output card address to it, or whenever you want to write into a memory bit, you can bring the output call and give the address of the memory bit to it. So I can say, and remember with the PLC memory bits, it's always denoted by the letter M. So I can say M4.0, which implies that I want to write it to a memory bit 4.0. So if I save this and I download, and I go to the simulator, I go online, you can see now whenever I get the conditions right, then I can then write into the memory bit either logic 1 or logic 0. At the moment, the memory bit is holding logic 0, and we can see that there's no tick here indicating that it's at. Okay, so to get the conditions right, then which means I have to turn off one of these AND gates for it to move to logic 0, and then the NOT have to invert it to logic 1 for our circuit to work. So I turn off 6.2, and we can see that it has been inverted. Immediately here becomes logic 0, the output of the NOT becomes logic 1, and then we can get an output going to right into this memory location 4.0, and we can see that it's ticked right here. So basically that's the purpose of the NOT gate, and then that is the purpose of our output card. Okay, so we move on to the next. I go offline. The next one is this output known as the midline output. So if you want to have a help, you can click on it and then you go to the help page, and basically these are what we term as the midline output. Now how do you use this midline output? So let's say for instance I'm writing a code and I want to get a result of all these 3 inputs, so that I can use this result somewhere within the code even before this output is energized. So let me delete this one and then create illustration. So I'll insert another network. So let's say I want to know the states of this particular input so that I can use it at this part of my program. There's 2 ways you can do that. The first is the hard way, which means you have to repeat all this particular input right here, and then you can then use it to energize any output that you want to. So let's say I want to energize an output, let's say Q6.1, and then to energize this output I want all these input conditions to be met before this output energizes. So one way to do it is to bring all this input here. The next is to make use of this midline output. So I will set a midline output here, and always when you insert a midline output, it needs to write its information to a specific memory location that you can fetch it to use. So I have to give it a variable name, which is a memory location to store its information. So I will give it M4.1. So giving it 4.1, I can then introduce M4.1 at this section of my code. So this one will come in as a contact, an input contact. So I'm using a contact of M4.1, which is M4.1 right here. Now let's save, download, and then simulate to see our results. I go online. Okay. So looking at our code, we realize that now we want the state of this to be read into this memory location, and then we can fetch it to be used somewhere else within our program. So when I click on 6.2, we can see that immediately this section of our code becomes healthy. So it's write logic 1 into this particular section, and then we can then fetch that information and transfer it to this section of our network, which we are using also to control another output. So basically that is the implementation or the use of what we term as the midline output. Okay, so from here I go offline again, and then we continue. The next on our list is going to be our reset set, but to explain this I need to introduce first the reset set and then set reset, and after that we can make use of this particular output calls, which is the reset set. So I'll insert a new network. Okay, so this is what we term as flip-flops. And flip-flop, just as I said from the previous tutorial, that flip-flops can keep one bit of information. So whenever I want to create a latch, I can use a flip-flop. But remember, we have two set of flip-flops here. One is S and then the other one is SR. Now the name comes based on priorities. So when we have a set reset flip-flop, which means the reset has priority over the set. So let's illustrate this so that we get a clear understanding. So I will select this line and then introduce my set reset right here. And remember, set reset must also keep an information, one bit of information. So you always have to give it a memory location where it will store its information. So I will store this information at M4.2 because I've already made use of 4.1 at the top and then 4.0. So I'll have this. So I'll introduce an input right here and then introduce another input right here. So this one I'll give it 6.3, give this section 6.4. So now I save, download. Okay, so I go online. And basically when I look at input 6.3, it's not checked, and then 6.4 is also. So we can see that I can then take 6.3 to turn it on. And then we can see that the set reset is set, and then it can remember that it's at logic 1 and it should stay there till we press the reset. Okay, so when I press reset, which is 6.4, it resets. Now let's see what happens if I click on the input 6.3 and leaves it on. Now the input 6.3 remains on, and then when I tick, which is the reset, let's see what happens to the output. We can see that the output has been reset. This is telling us that the reset has priority over the set. So whenever you want to have an application where you want your reset to have priority over the set, so that when the set signal still remains and the reset comes in, the output will then be forced off to save your system. So basically this is the illustration of our set reset, indicating that the reset always have priority over the set. Now let's move on. I'll go offline and then we'll look at our reset set illustration as well. So I will delete this one quickly. Click on delete, and then I'll bring our reset set. Give it the same address, M4.2, and then I can give this section I6.4. Okay, so I see, and then download. Okay, so I go online again, and then I bring this simulator. We can see that this is our reset set. So I go off on 6.4 and I go off on 6.3. So basically we can see that the 6.3 is going to reset our flip-flop, and then 6.4 is going to set it. So I will set, and then now let's see what happens when I press the reset whilst the set is on. So I press reset, and we could see that the set is having priority over the reset. So the output still remains at logic 1 even if the reset signal comes. So this is basically the function of the reset set. So any application where you want the output to still remain when you have both the set and the reset signal at logic 1, then you have to go in for the reset set flip-flop. So I go offline, and then we move to our next, which is going to be our reset and then set calls. So basically, how do you use this? So sometimes within your code, let's say I have this particular flip-flop right here, and it's another part of my section of my code, I would like to reset this flip-flop. But then I have two options. It's either the condition that I want to reset the flip-flop, I have to introduce it right here on the flip-flop line, or I still remain at this network and then into the reset call. So I double click on this one to insert the reset call, and then I put the condition to reset the call right here. So I put an input. Say if I receive an input from input I 6.5, I want the flip-flop to be reset. So then bringing this code, then I have to give the flip-flop reference address to this particular section so that I can be able to write to that particular flip-flop. So I'll say 4.2. Okay, so I save it, I download, I'll go online and then bring the simulator and then let's see. So we can see that in our simulation, our boot set and then reset it are on. So let me take the reset off and then the set off. So our flip-flop is still at logic 1. So now let's say I want to reset this flip-flop at this section which of my code. Okay, so I'll click on 6.5 and see whether the flip-flop will reset. So I go to 6.5 and we can see the flip-flop has reset. So basically that is the application of this reset. The set also plays the same role. So at the point where you want to set the flip-flop at other sections of your program, then you can bring on the reset call and then use the conditions that you want it to be set in front of it, and then you can send command for it to be reset, giving it the same address position. So we are done with this. I'll go offline again and then we move on to the next item. Okay, so the next item on the list is going to be our edge detectors. We term this one as one shot instruction, or falling edge and then rising edge detection. So basically, how does this thing work? Let me set a new network, Control I, and then we will illustrate how this thing works. So let's say, for instance, at a certain part of your code, you want to only read the transition of input signal or a memory bit because it's moving from logic 0 to logic 1. You want to only see the rising edge of it, then which means you need the positive edge trigger instruction. So P means positive edge trigger. So whilst the signal is transitioning from 0 to logic 1, the system will detect it, and when it reaches logic 1, it does not care whether it stays at logic. It will only generate a pulse to trigger your system during the transition period. Okay, so when we talk about the N, that is the negative edge trigger, which means it will also detect only when the signal is moving from logic 1 to logic 0. So which means it's the negative edge that is it will be detected. So let's apply this in an example for us to get a clear understanding. So let's say, for instance, I have this flip-flop, and then in this flip-flop, this input comes and this input will stay, but then I want other sections of my code to also have access to bring the reset signal, so that this input does not constantly reset this flip-flop for me. So I just want a one-shot reset, and then it should release the reset button so that the flip-flop can be set again by other sections of my program. Then which means I have to introduce an edge detection right here. Okay, in this case we will use negative edge detection. So I'll double click on it, and remember they also need memory locations to store information, so you still need to give it a memory address. So this one is going to be M 4.6. okay, and then on the set I would like to put a positive edge trigger right here, and I give it M 6 dot, sorry, 4.7. okay, and then we have the input condition that is going to set this particular one. Let me delete one, let's double. So that is going to be I 6.5. Sorry, 6.5 is used somewhere else, so let me use 6.6. So I save it, download, online, and then I bring the simulator, and then we have a look. Okay, so we can see that currently the 6.6 is off, and the 6.3 is also off. So let's say if I want to set the flip-flop, I have to press the 6.6 and then I press 6.6. So we can see that the flip-flop, immediately I press the set the 6.6, the flip-flop is set, but you can see that the signal, which is the 6.6, is still active, but you can see from here that it's broken. This is the purpose of this edge detection. So which means this P was able to detect whilst I was transitioning from 0 to logic 1 and set my flip-flop, and then after that release the flip-flop set so that other sections of my code can also make use of this set pin. And then let's see the reset as well. You can see that because this one is a negative edge trigger, when I click on 6.3, nothing happens to my flip-flop until I untick, which means it will be able to only detect when I'm moving from logic 1 to logic 0. I untick and then immediately it resets my flip-flop. So basically that's how the edge triggers or the edge detections work. So you use the negative edge detection whenever you want to read signal, the transition of a signal from logic 1 to logic 0. Okay, so with this explanation, we will now move on to the next one. The next one is our save instruction, and then another negative edge and a positive edge trigger. But we'll look at this one in another tutorials into details. So for now, we are done with the bit logic. We'll then minimize the bit logic, and then we will move on to our comparator. To do this, I have to go offline again, and then I can now drop comparators. Okay, so I'll clear my program quickly, insert a new network, and then we can talk about comparators. Okay, comparators is basically where within your program you want to compare variables or you want to compare integers. So when we come here, we can see that we have different types of comparators here. We can see this is an equal to comparator, and under it we can see underscore I, indicating that this can compare integer values. Now the one underscore D means it can compare double word value, and the ones underscore R means it can compare real values. So now let's bring one comparator into our network and then have a look at it. Okay, so this is equal to comparator, and then we can see that if we put a value here, then we can now compare that value to the value at input 1, and then we can output something, and then we can use this output to control certain section of our code. So let me bring an output signal here, and I say this one can go to output. Okay, this is 6.1, and then I'll give it values that we want to compare. So for this section, I say I can key in 100. So I give it a fixed value, and I say that we always want to compare this fixed value to a variable value that I'll put in. So this one I'll give it a memory location so that we can vary it on our simulator. So this is an integer. Integer is 2 bytes, which is a word. So I will say memory word. W means word. So memory word, which is representing 2 bytes. So memory word, I'll use memory word 6 for this particular illustration. So I save this, save and download, and then I can go online with my simulator. So we can see that right here I can have a value 100 here, and then my output is off, is waiting for us to get an equal to value at the memory word 6, and then it can compare, and if they are equal, it can output something for me that I can use somewhere else within my program or to control other flows within my program. Okay, so I will insert a memory word. I will insert, let's say, insert bit memory, and then I have to change this portion to W because it's a memory word, and then immediately change to this. Now this is decimal. Remember we are dealing with word, so I will change and go to, sorry, we are dealing with an integer, so I will go to int, and then we can see that if I enter the value 90, sorry, this is a memory word 0, I have to change this one to 6 because I'm dealing with memory word 6. I enter the value 90. We can see that 90 has appeared here, but 90 is not equal to 100, so we have nothing at the output. So now I change and then enter 100, and we can see that immediately I entered 100, it has been able to compare and give me an output. So let's say, for instance, if I want to compare temperatures, so that it reaches a certain value, I want to trigger a fan to come on. I can use this particular arrangement to do that. So I can use this output to turn a fan on whenever the temperature reaches a certain preset value. Okay, very good. So basically, this is a test for an equal to comparator. We can move on to the next one. So I'll move to a double word comparator for us. You can try the other ones, equal to, less than, or equal to. And if you want help, you can come here, click on it. You can have the help instructions right here. Okay, so I'll insert another network, and then I'll bring the double word, which is also still an equal to, but this will compare double word. So here also I'll insert a value, let's say 20, and then here I have to give it an address. But because this is a double word, I have to enter memory double word, so D. And then this one I'll move memory by 6, which means it will cover bit 6, bit 7. So I'll move to memory double word 8, and then I can then save. Sorry, I need to enter a call. So I enter a call, which is going to my output kill 6.2. I can then save, and then I can go here. I can then change this one to my memory word 8. Sorry, memory double word 8, and change it to double word. And now I have to change here, it's no longer an integer, but it's a real. Sorry, it's supposed to be a decimal. So 20. And we can see now the output comes on. So basically it's supposed to be a decimal because it's a double word. So decimal, double word are 2 words. So we can see that immediately I enter 20, the output comes on, and I can use to control something else in my program. Let's move to 10, and then we can see it goes off. So this is a double word comparator. I'll go offline and then insert a new network, and then we can try the real comparator as well. So I'll move to real comparator. Okay, so I'll put a value here to compare because real is basically a number with a decimal point. So I will say 100, 0, being my fixed value, and what I want to vary to do a comparison will be my memory, and it will still be my double word because real is also 4 bytes, which is 2 word. Okay, so MD, so I've used 8. So if I use 8, because 8 is 4 bytes, it will use 8, 9, 10, 11. So I have to move to 12. Okay, I save. Sorry, I have to insert the call. And this is going to be my 6 dot. Can say 4. Sorry, Q. 6.4. Okay, then I can save. Download. I can go online and then bring my comparator. Okay, so I use the same site, and this is going to be my 12, and then I change this to real. Okay, so now I'll enter my value to compare. It was 100, so if I enter 100.0, you can see the output comes on. And if I enter 90, it goes off. So basically it's working perfectly. So basically that's how you use comparators. So we have an integer comparator, double word comparator, and then a real comparator. So from here we move on to the next section. So we've done with bits logic, we are done with comparators, we will now look at converters. So it comes to a point within your program that you need to convert data types from one type to the other. That's where this section becomes a bit handy. So we have BCD to integer converter right here. We have integer to BCD converter. We have integer to double integer converter, integer to real converter. So if you want to read more on it, you can click on the help, double click on it, and then you can have illustration of how these sections work. But we'll pick one of it for an example on set, and then we can see that we have double integer to real or integer to double integer. So I insert this one, which means I have to put an integer value right here. So I'll put an integer value 100, and I'm expecting this one to be converted to double. So I will have to write this one into a memory location that we can have a look at. I've made use of 12, so 12, 13, 14, 15. So I have to then move to 16. So this is MD 16. Save, download, and then we change here to 16, and then I'm reading double integer, and then go online. We can change your view right from here. So auto. So we can see that here is 100, but you can see the number of zeros that is being added at this point up to this 100. So those who do a conversion for you, this becomes handy when you are applying this particular value to a certain section of your program where the block cannot accept integer. Then you need to convert it to a type that is acceptable. So for now I don't have a real example, but as we move on in the tutorial we will come across this particular conversions a lot, and basically this is where we'll be using most of the function. And at other points within our program we'll also create our own converters that will also aid us to do other conversions. Okay viewers, this brings us to the end of this section of my tutorial series. Thank you very much for watching. Please subscribe and press the bell icon so that you will receive notification whenever I generate new tutorials. Thank you all. Bye bye.